All set. Thank you. Thank you. We have 1 minute. Thank you, sir. All right, thank you. Thank you. Okay. About 10, 15 seconds. Yeah. Okay. Okay, that's time. I'll take what you have. Thank you. Thank you. Anybody else here? Thank you. Thank you. Anybody else? All right, so let's take a look at it. On the first one, you've got to do a quotient rule. But while you're doing the quotient rule, you have to do a chain rule in the middle of the process. So let's just see here. We've got, the top over the bottom, right? So the derivative of that should be the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared. That's just the quotient rule formula. And now I just start taking derivatives. So derivative of x is 1. Leave this one alone. Minus. Now this is the one that requires the chain rule because you've got a function inside of another function. So the derivative of the square root of something is 1 over 2 times the square root of that something. That's this. Chain rule says now multiply times the derivative of what's inside. And the derivative of this, you do those separately. So derivative of x cubed is 3x squared. Then derivative of 1 is 0, so there's nothing there. Then you have to multiply by the x there. All of that over the bottom, which was a square root, but you're squaring it, so the root goes away. I would accept that, that's fine. What I did here, all I did is just took this, made this 3x cubed, slid it on top. And there's more algebra you could do, but that's good enough. Now on the second one, we have composition, right? This is chain rule, but we have 3 layers to this onion, I guess. We have an outer layer is sine, the next layer in is a square root, the next layer in is this little polynomial. So you always start with the outside. Derivative of sine of something is cosine of that something. Chain rule says now multiply times the derivative of what's in here. Derivative of this is, well, you've got square root of something. So kind of like the previous problem. 1 over 2 square roots of that something. And you're done with the root. Now you take derivative of what's inside there, and that's 2x plus 1. And then all I did here is I took this cosine, slid it on top with the 1, brought it on top, and I put the 2x plus 1 in front. This 2x plus 1 has to be in parentheses, or else it's wrong, right? All right, any questions on that? Yes?
Is there like a preference that you have when squaring or rooting and like putting it in the denominator opposed to this half as the exponent? Like, is there a certain situation that you prefer to put it as the exponent opposed to it like when it's a fraction and it's in the fraction?
Are you asking me like,
Yeah, when you convert, like instead of x squared plus,
hold on, I'm not sure I understand, so let me see if I'm, are you asking me like this versus this or no?
the equation on the first one to the prime of the second, well, the one on the other side. Is there a preference? Well, the one on the left side of that.
This.
Yeah, is there, but the equation, those are the same thing, yeah, that, and then.
These two are exactly the same thing.
No, but, okay, so the one on the upper, yeah, that, and then the one on below, but on the left-hand side.
What about it?
They're not the exact same thing?
Well, this is saying take the derivative of the square root of x, right?
Mhm.
That's this,
That's
or
what I'm
this.
saying. Yeah, minus, well, if you take away the, here, I'll ask you, I'm saying, is there a preference in times when you use the exponent opposed to the fraction? Still not, okay, I'll just ask you.
No, I'm trying to, does anyone understand the question?
He's basically asking if you care whether you write it as the top right versus the bottom left.
Versus the bottom left?
Yes.
Well, you haven't taken the derivative here,
Yeah.
right?
So, yeah, if that was, but if it shows, on the top. So, yeah, you
So-
need the equation of the top and bottom. Yeah. One's a derivative,
Square
one's
root.
not.
Yeah.
Is there a time where you prefer us to write the square root out rather than the to the power of 1/2?
Yeah, I mean, I don't know if that's the question, but you should be able to go either way. You should be comfortable going rational exponents versus radical notation. Those two are interchangeable, but I always prefer to do the square root. Whenever I have a square root and I take a derivative, I prefer this notation. When I get to something like cube root, fourth root, I like rational exponents instead because the rule isn't as simple as 1 over 2 root x, right? What's the derivative of root x? 1 over 2 root x. To me, that just kind of is automatic. So I personally don't care as long as it's right. I think if you were going to, like imagine that we had to, well, not this one, but the one before. Imagine we had to take this, because this will be coming. What if we had to set that equal to 0 and solve, right? So one of the first things you would do to set this equal to 0 solve is you'd put these two fractions together with a common denominator, right? So if I had rational exponents, I'd have things raised to the half power or negative 1/2, and I'm not sure how comfortable you'll be with that. I mean, you can do it, but I think it's easier to work with this if I had to put these two together. Put those two together, all I'd have to do is insert this 2 root x cubed plus 1 on the top and bottom, like this, so that they have the same denominators. And then do you see how this is real nice? Because when we multiply those together, the roots go away. Yeah, if you had half powers, I don't know how that would work out for you. It would work out if you were good with your algebra. It should all still work out, but it just might not be as easy to see it.
Gotcha.
So.
Yeah, I was just asking if there was like a scenario where it's less work for the exponents, or if there's a better scenario.
No, I think it's really, you should be able to be interchangeable with it. You know, don't get married to one notation over the other. Treat them both the same. Like, have it in your arsenal. All right, so I hope that quiz was not too crazy. So today we are going to continue. Actually, I haven't looked at our calendar in a while to see where we are. Where are we? Are we behind? Please don't tell me we're behind. Or 2 behind. Yeah, we might be a little bit ahead right now because I moved through that chain rule pretty quick. No, are we? Oh, okay. So today is the 27th? Yeah, implicit and...
We don't have to come on July 4th?
You don't have to come?
We already started.
Yeah, we have a holiday on the 4th of July. So, yeah, no class. I won't be here. You can come. Campus will be closed, but...
Did we finish implicit differential?
Now I'm going to do a little bit more implicit differentiation today, just a little bit in the front end, and then we're going to get into related rates. All right, so last time, the main takeaway from last time is that sometimes we have equations that we can't solve for one of the variables explicitly, like get y equals and then a function of x on the other side. And when that happens, we need to have this technique for finding the derivative still, finding the slope of the tangent line. So we introduced this idea of implicit differentiation. So I'm just going to pick a problem here out of the homework. Let me see here. Here's a good problem for us to do. I'll do number 24. So this problem is, they give you a curve y squared times y squared minus 4 equals x squared times x squared minus 5. And then they give you a point. They give you this point 0, -2. And they even give you a drawing. I'll do it off camera over here. They give you a drawing of what this looks like if you were to graph it. Oops. If you were to graph it on a computer, it looks kind of like a figure 8, and then this side goes like this, and this side is symmetric, goes like that, something like that. All right, that's the graph of that that equation, that relationship between x and y. So it's a curve on a flat sheet of paper. We've got a curve, and so what we'd like to know is if we went to certain points on this curve, could we find the slope of the tangent line? So we want to find. Here are the instructions. Find the equation of the tangent line at that point. And we talked last time about when you have an implicit equation like this, that in order to talk about the slope of a tangent line, we're probably going to need to know the x and y value. We're going to need both the x and the y so we know exactly where we are on the curve. So let's get to this. So to find the equation of the tangent line, right, find the equation, we know that eventually we're going to need to get to this y minus y1 equals m times x minus x1, this very important formula from college algebra. This gives us the equation of a line. All we need to know is a point. Do we know a point? We know the point, right? We know 0, -2. The only thing we need is the slope, but this here we're talking about the slope of the tangent line, which for us is dy dx. It used to be y prime, but the problem with y prime is that it didn't show us the independent variable. So we switched away from this notation in this section on implicit and switched to this notation. So we're going to differentiate this equation on both sides with respect to x. Now, I have to make some decisions before I do this derivative. Do y'all see the differentiation involved here? We have a product between these two, don't we? And a product right there. So we could have to use product rule, right? But do y'all see that I can just distribute that through? Just distribute. Why don't we do that? Let's distribute. I think that'll make our lives easier, because then I don't have to do product rule. Y to the 4th minus 4y squared equals x to the 4th minus 5x squared. I think that's a little easier to work with, don't you? Instead of using a product rule. And now the derivative. I take the derivative with respect to x on the left side, and then the derivative with respect to x on the right side. And because I have subtractions between these, I can do these individually. So let me go ahead and do that. I'll come back to this. So this becomes the derivative with respect to x of y to the 4th minus the derivative with respect to x of 4y squared. Notice how I put that negative in between, right? Negative in between. And then equals the derivative with respect to x of x to the 4th, and then minus the derivative with respect to x of 5x. Sorry, I'm off the screen there a little bit. Squared, oh yeah, thank you, squared. All right, so now I differentiate each one. And I have to use this new kind of style of differentiation where I'm constantly using the chain rule on everything. So when I take the derivative of y to the fourth, I'm looking at that as like the eraser to the fourth power. The derivative of that should be 4 times the eraser, which was y, to the third power. So that's just like a power rule on that. But then the critical part, you have chain rule here, so you have to multiply that times the derivative of what the eraser was. And the derivative of y is not 1. The derivative of y with respect to x is exactly dy dx. I'm going to write it this way. I'm taking the derivative with respect to x of that y that was here. And that will turn into dy dx. And are we happy to see that? Mm-hmm. Yeah, because that's actually, that is the slope of the tangent line, right? Dy dx. So we need it to appear. It just did. All right, so let me just write below this. We're at 4y cubed times dy dx. Okay, minus. Now let's talk about this one. I need to take derivative of that, 4y squared. Well, 4 is a constant attached to the function. So I already said that when you take a derivative of a constant by itself, it's always 0. But if it's attached to the function, it will come for the ride, right? So the 4 is going to come down here, and then I'm going to do the same thing I did on the y to the fourth, but for that one. So the 2 will come out, hit the 4, become an 8, y to the first power. So that's that 2 coming out, hitting the 4. Now I have y to the first power. Again, chain rule. Take the derivative of the y. Is that all right if I just do dy dx? Okay. Just as a little heads up, on the homework, I go like super shortcut, and I actually do write y prime here instead of dy dx. Just, it means the same thing. I just write y prime instead on some of the homework solutions. So if you're like, what in the hell is he doing? It's just to make the writing a little bit easier. All right, what about this one? We're on the other side of the equation now, right? Derivative of x to the fourth, 4x cubed times dx over dx, right? The derivative of x with respect to x, which is going to turn into a 1. You don't need to write it. I'm just doing it because make sure everyone understands we got chain rule going on here. Minus, pardon? Oh, okay, sorry. Yeah, so we have a constant in front here. So the 2 comes out, hits the constant, becomes 10, x. And then again, chain rule, dx, dx. Hey, just out of curiosity, are y'all seeing that anytime you differentiate something that has a y in it, at the end you're going to have a dy dx? And anytime you differentiate something with an x in it, at the end you're going to have a dx dx, right? It's kind of like this is always, the chain rule is always going to pop one of these out on the ends. It's just a question of do they turn into a 1 or do they not? So here I am. I have 4y cubed dy dx minus 8y dy dx equals 4x cubed minus 10x. There, those dx dx's just go to 1s. And that is the raw implicit differentiation. Now, fortunately on this problem, I'm asked for the slope of the tangent line. So to find the slope of the tangent line, I just need to know what dy dx is, but I need to know it at this point. So that means I can take this equation and I can replace x with 0 and y with negative 2, right? I could do that right now. Replace x with 0, y with negative 2. All right, I'll let you do that if you want on your own. But this step that I'm about to do, you would not have to do for this problem, but I want to do it anyway, because what if I had not asked you for the equation tangent line? What if I had just asked you in the beginning of the problem to find dy dx? Yeah, if I asked you to just find dy dx, then you would actually have to solve for dy dx here, wouldn't you? So I want to show that step just to get some more practice, even though it's not necessary for this problem. So I make sure I've got all my dy dx's on one side, everything that doesn't have dy dx on the other, which I already have. So I'm going to factor out a dy dx like a GCF, greatest common factor. Leaves me with 4y cubed minus 8y equals 4x cubed minus 10x. And once we factor out that dy dx, I can divide through by everything here in parentheses on both sides. I've got dy dx is 4x cubed minus 10x over 4y cubed minus 8y. That's what dy dx is. Now, I'm going to use that now, and I'm going to replace all my x's with what? Oh, that's going to be easy then. I'm going to replace all my x's with 0 and all my y's with -2. So look, I'm going to say, watch how I write this. At the point 0, -2, dy dx equals, well, what does the top turn into if I replace all the x's with zeros? 0. And on the bottom, if I replace with -2, I don't get 0, do I?
Nope.
No, I just get some number, right? Okay, so it's a number. I'm not sure what it is, but it's not 0. So that means our answer is 0, right? Our slope of our tangent line is 0. Which you should have gotten that same thing had you plugged in over here. Okay, if you plugged in 0 for x and replace your y's with -2s, you should have still got 0. So I know that the slope of the tangent line is 0 at that point. So now what I can do is I can write the equation of my tangent line. So final answer is y minus y1 was -2, so y plus 2 equals the slope 0 and then x minus 0. Yeah, like that. And the whole right side is 0. So y is -2. And again, recalling from college algebra, this is the equation of a horizontal line through the y value of -2. So it's probably this one right here. It's probably the tangent line right here. The graph looks like this. So I believe that's the point 0, -2. And so I think you would agree that the slope of the tangent line there is 0, so the equation of the line should just be y is -2. Okay, so on a test, if I ask you for the equation of the tangent line, then when you get to the point that you've differentiated, where was it, right here? Then you just replace x and y with your numbers. You don't have to solve for dy dx. Don't waste your time. But if I ask you for dy dx, then you have to go through the actual, like, getting the dy dx by itself. So it's actually more work. You follow?
When we put 0, -2, we don't have to worry about dy or dx in that equation, right? We just plug it
When I put 0, yeah, so when you put 0 here, this is all 0, right? And then -2 cubed is -8. Times 4, that's -32 dy dx. Minus -2 in here, it turns into a plus 16 dy dx. Still with me? Equals 0, right?
Yeah.
And then now put those two together, you should get -16 dy dx equals 0. And then divide both sides by -16.
Oh, yeah.
And dy dx is 0 still. All right, one more and then we're going to move on. One more, maybe two, but probably one. All right, this is an interesting problem here. Which one do I want to do? All right, let's do this. X to the 4th plus y to the 4th equals 16.
Which number is this?
I'm kind of modifying it. This is number 28, but I'm kind of modifying it a little bit. So here's an implicit equation. Here's what I want. Find y double prime. Find y double prime, the second derivative. All right, now, using Leibniz notation, this means the derivative. How do we do it with Leibniz if we want to do a derivative twice? It's dy dx, but there's something we have to do here. Do you all remember? You have to put a 2 and you offset it, right? You put a 2 here and a 2 there. That way you don't think it's squared. That's the way you write the second derivative, right? Okay, fine, whatever. We know we have to take derivative twice, right? All right, let's start with the equation. I'm going to start by differentiating both sides with respect to x first. So in other words, I'm kind of like taking the derivative, the first derivative, just the derivative the first time. On the left, I can split it into 2 because there's addition between those. And on the right, well, I'm not going to do any more work. That's 0, right? Derivative of a constant is 0. Let me keep going here. This is just 4x cubed. Now, I didn't write it this time, but there really is a dx over dx here, isn't there? Right, the 4 came out, x to the third power, and then times the derivative of x with respect to x. So there's a 1 there. I didn't write it. Plus, do y'all want me to write it or no?
No.
No? Okay. What about this one? 4y cubed. This one you do need the dy dx. And that's because we don't have dx over dx, we have dy over dx. And that equals 0. Everybody good? Yes? Okay, look, I mean, there's a lot of things we can do right now. My first instinct here is that, do y'all see they both have 4s? Could I just divide everything by 4? I could, right? I don't have to, but are y'all all right with me doing that? I mean, it doesn't have to be done, but if I divide everything by 4, it just might make my life a little easier. Divide the right side by 4, nothing changes. So that's just a little cleaner looking, right? It's a little cleaner. Yes?
You don't have 4 dy dx. Why doesn't that matter?
It's multiplied. Because there's multiplication between the two, the 4 just reduces out from one of them. Right, you're basically doing this. Divide by 4, divide that term by 4, the 4's reduce. Become a 1. All right, I need the derivative again, don't I? So what I'm going to do right now is I'm just going to take derivative again. So watch the way this notation works. I'm going to take the derivative with respect to x again on the left. And then equals the derivative with respect to x again on the right. Right? If I take the derivative again, I should get a second derivative, shouldn't I? Okay, the right side's the easy part. Derivative of a constant is still 0, right? On the left side, I have 2 terms separated by addition, so I can write it this way. When I just said I have 2 terms separated by addition, that's kind of redundant because to be terms means that there's addition or subtraction between them. But I'm just being clear. These are 2 terms. I've got addition. I can do derivative of each one. Now, the one on the left becomes what? 3x squared. That's it, right? 3x squared dx dx, but we're not going to put the dx dx? All right? Let me leave that right there. So we have 3x squared and then plus, okay, here's the tricky part. Because what do we have? We're taking derivative of a product. Do y'all see it? That's multiplication. That's multiplication. So how do you do the derivative of a product? You use the product rule. All right, so let's see if you can do this. We got to take the derivative of this times this. Let me say it again. Derivative of this times this plus the derivative of this times that. Let me write that down. I need to take the derivative with respect to x of y cubed, okay, that's the derivative of the first one, times the second one, plus, now the derivative with respect to x of dy dx, like that. So I'm taking derivative of the first one times the second, plus the derivative of the second times the first one. Everything you see here, is our product rule, right? Rule being applied to this right here. Any questions on that? I mean, I haven't actually done these derivatives. I'm just writing down the formula. Derivative of the first times the second plus derivative of the second times the first. What now? I'll take derivative. Let me finish writing out the thing, though. What is it? Equals 0, right? Okay, so equals 0. All right, let's do some derivatives. This 3x squared's here. Nice and pretty. Okay, what is the derivative plus? What is the derivative of y cubed? With respect to x. 3y squared. Yes. dy dx, right? Don't you have to do a chain rule, just like you did before? Okay. 3y squared dy dx. That's the derivative of this. Right? Times what? Times dy dx. Times, right? Times dy dx. That's multiplication between all those. Plus, now, this piece right here. What do y'all think this is? The derivative of the derivative, right? That's not a multiplication. That's the derivative of the derivative, which is the second derivative, which is what we're trying to find, right? So this is going to be, the way I'd write that in red, I would write d square y over dx squared, like that. That's the second derivative. That's this piece in red, times y cubed equals 0. Who has questions? I'm not done, but any questions on that? Yes? Yeah, I was hoping you would ask.
Is that another second derivative?
Yeah, so is this a second derivative or no? What is this? This is the first derivative times the first derivative. So it's the first derivative squared. The second derivative is not the first derivative squared. The second derivative is the derivative of the derivative, right? So this is actually just the first derivative squared. That's the second derivative. And then, yeah, so let me rewrite this. I'm going to write 3x squared plus 3y squared. This is getting tedious. I have to write this way. dy dx squared plus d squared y